This is video 35 in our series Analytical Mechanics. The playlist for all the videos is at the website digital-university.org. In this video, we're going to consider the motion of a billiard ball when it has been struck at a certain distance h above its center, or above its center of mass. And here in our system, moving to the right is positive, and clockwise movement is also positive. Going to the left and counterclockwise is negative. Now, what we want to consider is this. When we hit the billiard ball with overspin, that is where the cue stick strikes at some distance above the center of mass, it will have a linear velocity and an initial angular velocity as well. And it will then sort of slip and slide over the surface. At some point later in time, we reach a state where the linear velocity of it equals the angular velocity times the radius of the ball. We discussed this in videos 33 and 34 and 32 as well. And then in video 30 we discussed pure roll, which is what this is. So we strike the billiard ball up here. It has a linear velocity and an angular velocity, and it sort of skids across the surface. Then there comes a time where we have this relationship and it goes into pure roll. Now, in video numbers 32 and 33, we had considered what happens when you hit the billiard ball right in line with its center of mass. And then when you do that, it has a forward linear velocity, but no angular velocity. But after time, it did develop an angular velocity because of frictional torque acting upon the ball, and then it went into pure roll. When it did go into pure roll, at that time, the velocity of the ball, its linear velocity, was equal to 5/7 of its initial velocity. It was less than the initial velocity. Now when we hit it above the center of mass, when it goes into pure roll, it can be greater than the initial velocity. And we want to know, what is the height above the center of mass that we have to strike the billiard ball, so when it does go into pure roll, the velocity at that time equals 9/7 times its original velocity. So when it goes into pure roll, its linear velocity is greater than what it was at the time when it was struck by the cue stick. And we're going to analyze that problem by considering the angular momentum of the ball about different reference points. And the first reference point that we will consider is right here where the cue stick strikes the ball. So let's call that point C, and we want to consider what will be the angular momentum of the billiard ball about this point C. Before we do that, let's ask ourselves, what would be the torque about point C? Now, torque, in general, is a cross product between a position vector and a force. Now, in this case, the force is right at point C. So the position vector is 0, so the torque at point C is 0, which means that the angular momentum at point C is not 0. Let's get rid of that. It might be, but it doesn't have to be. It is a constant. and that's because the time derivative of momentum is the torque. And if this is 0, the derivative is 0, therefore the momentum is a constant. So about this point C, if we consider the angular momentum of the billiard ball about that point C, it is conserved. Now, let's consider what is the angular momentum of the billiard ball about point C just before it is struck by the cue stick. Well, at that point it's just sitting still, so the angular momentum is 0. And now we want to consider the angular momentum about point C just after it is struck by the cue stick, when it has this linear velocity and that angular velocity. So we'll call it LC-A after the ball was struck. Well, even though it has these two velocities, this is still 0. Because the angular momentum about point C is conserved as constant. So if it starts out 0, it has to remain 0. But there's more to the story than that, because remember what we talked about in video 33 and what we actually derived in video 19 is that when you consider the angular momentum of an object about a particular point, that angular momentum has two components to it. One, here we have an object, and assume that it has a linear and a rotational velocity, and we want to know, well, what would be the angular momentum of this object with respect to point O. The first component is the angular momentum of the center of mass with respect to point O. And that's just the position vector r cross the total mass of the object and the velocity of the center of mass. The second component of angular momentum for the object about point O is the angular momentum of rotation about the center of mass. And this second component, that is always equal to the moment of inertia about the center of mass times the angular velocity of the object. So, with this in mind, let's take a more closer look at the angular momentum about point C just after when the ball is struck. Before it's struck, it's just sitting still, so there's not much to talk about. Well, here, it does have linear velocity and an angular velocity. So the first component of it is the angular velocity of the center of mass with respect to point C. So we need a radius vector here, and that radius vector is, of course, just, or not a radius vector, but a position vector, and that position vector is just the radius of the circle. So we have it like this. Point C, here's the center of mass, here's the position vector from point C going to the center of mass. It's just the radius of the circle. And we're considering now the angular momentum about point C when the billiard ball has this linear velocity and that angular velocity. And the first component, the angular momentum of the center of mass about point C, that is just r cross mv naught, which we have right here. Now let's see, here is r. Then pointing to the right is mv naught. When we position the vectors, take the cross product, though, we do it like this. So here's r, here's mv naught, and that cross product is going to be r mv naught, those magnitudes, times the sine of the angle. r times the sine of this angle is just this vertical distance, h. That's this vertical distance, h. So this, in terms of magnitude, is just h mv naught. Now, is this positive or negative? So we go back to here. Here's r, here's mv naught, and we wrap our fingers around it. The thumb points up, and the fingers are going like this, counterclockwise. Now, for our system, moving to the right is positive, and clockwise is positive. Counterclockwise is negative. So this component of the angular momentum about point C, just after the ball is struck, that's negative. The second component is just this, the angular momentum of rotation about the center of mass, and it always equals this expression. And here, omega naught, that's positive. That's going clockwise positive. So this is positive. So the angular momentum right after the ball is struck at that point C is this minus this. Now, remember, before the ball was struck, it was just sitting there. So the angular momentum was 0. Well, after it's moving, when it has these components of a linear velocity and angular velocity, it is still 0, because we have the conservation of angular momentum about point C. So these two different components of the angular velocity, there was a positive component and a negative component, and they subtract each other to equal 0. Or this equals this. And we'll make use of this equation here in just a few minutes. Don't forget it. So here then we've considered the angular momentum of the billiard ball about this point here. Now let's consider the angular momentum of the billiard ball about this point here, C, right where the billiard ball makes contact with the surface. And let's consider it immediately after the billiard ball is struck by the cue stick. So immediately afterwards, it has this linear velocity and this angular velocity. This means now it's going to be sliding across the surface in this direction, so there's going to be a friction in the opposite direction. Now here, as it rolls right into the surface that the ball is sitting on, that too will have a little bit of friction too in the opposite direction. It's rolling into in this direction, so there will be some friction in this direction, but it's going to be a net frictional force in this direction. Now before we consider the angular velocity about point C, let's consider the torque about this point C. Torque is equal to the cross product of a positional vector and a force. This time it's the frictional force. But the frictional force is right at the point C where the ball makes contact. So the position vector is 0. The torque here is also 0, which means that the angular momentum with respect to this contact point C is constant. Now, let's consider the angular momentum about point C immediately after that the ball is struck, when it has this linear velocity and this angular velocity. We'll call that the initial angular momentum. Then, at some time t, the ball goes into forward roll, or not forward roll, but pure roll. And at that time, it has a certain velocity. We'll call that Vf. And when it goes into pure roll, that is equal to r times the angular velocity at that time. That's the relationship for pure roll, as we talked about in video 30. So then it will have an angular momentum at that time, which will have a different value than this. Or is it a different value? Angular momentum is conserved. So whatever it was here initially when we had V naught and omega naught, it has to be the same when it goes into pure roll at that time when it has a linear velocity of Vf different than this, and a linear velocity Vf and an angular velocity omega f, each of these different from these. But right now, let's do this. And the reason why, of course, is because this is a constant, because the torque about point C is 0. Now, let's ask ourselves then, what is the angular momentum at point C, this point C, immediately after the ball is struck by the cue stick when it has this linear velocity, that angular velocity? So it has two components. The component of the center of mass with respect to point C plus the angular momentum of rotation about the center of mass. That's this. But let's go back and talk about this first component, the angular momentum of the center of mass about this point. So that's going to be, we need a position vector. It's just the radius of the circle, and then here's mv naught. So it's going to be r cross mv naught. This is 90 degrees, so it's just r mv naught in magnitude. Is it positive or negative? Well, here's r, our position vector. V naught goes to the right. We position it like this to take the cross product. Then when we do, our thumb points in, but our fingers wrap around in a clockwise direction. That's positive. So this has a positive value. And then the second component, that's just the moment of inertia about the center of mass times the angular velocity at that time. And that is just omega naught. So here, with respect to this point, immediately after the ball is struck, when it has this velocity and that angular velocity, the angular momentum about point C equals this plus this, which we have written out right here. But now remember what we derived a few moments ago concerning this. It equals this. So let's substitute. And we have, this is the expression then for the angular momentum about point C immediately after the ball is struck. And we started out with this, and we got to here because of what we derived a few minutes ago. But let's consider, for the moment, consider this as an expression for the angular momentum about point C immediately after the ball is struck. Now, what will be the angular momentum about point C, we call it the final angular momentum, when the ball goes into pure roll, when it has this velocity Vf and this angular velocity omega f? Well, that expression is going to be the same as this, except we're going to have V final here and omega final here. which we have written out like this. Now, two things to remember. This is when it's in pure roll. So for pure roll, we have this relationship, and also we wanted to determine what value does h have to be so that the final velocity when it goes into pure roll equals 9/7 of its original velocity, v0. Okay. Keep this term the same. This, the moment of inertia, is 2/5 mr squared. Omega, well, that would just be v up divided by r. So we have it like this. This and this cancel, so we have rmvf plus 2/5 rmvf. These canceling. We're added together, we have 7/5 mvfr. That is then the angular momentum when the ball goes into pure roll. And we wanted to have it specifically close so that this has this value. So let's put that in place of this, and we have this equation. These cancel, so finally we have this. This is the angular momentum about that contact point C when the ball goes into pure roll. But this, remember, has to equal what it was initially, because about this point C, angular momentum is conserved. And remember, this was this, which has to equal this. So we can cancel out mv0, 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 and we have r plus h equals 9/5 times r. Right here, or h equals 4/5 r. So what we have finally learned is that if we strike the billiard ball with the cue stick at a distance 4/5 its radius, then it will have the initial velocity v0 and angular velocity omega naught. When it goes into pure roll and we have this relation, then the velocity, the linear velocity at that point, will equal 9/7 what it was originally. As you could see, we could derive that then just by considering the angular momentum of the ball with respect to different reference points.